Hello, this video is to cover the reactions of alcohols and haloalkanes. This is from a June 2010 past paper, but the content is still relevant. So the question starts off with a flowchart centered around butan 1-ol, and you have 4 different combinations of reagents and conditions, and you've got to give the product form for each of these, 4 marks, so you know it's going to be 1 mark per answer. There's nothing specific in the question that says the format that they want the answer. So although you've got the structural formula here, you could give the structural formula, but they also accepted the name, the skeletal formula. Now, the very first thing that I'm going to do for any of these sorts of things is get the displayed formula, because it's really going to help. The structural formula, you can miss some things. Drawing it out, really make sure you can see where it's going. And of course, butan 1-ol, they did give you the name, but the key, it's a primary alcohol. So one of the first things you need to remember about alcohols is oxidation. Having a look at the 4 sets of reagents, potassium dichromate, that is our main oxidizing agent for alcohols, and oh look, it features twice. So distillation once, reflux once. You know, hopefully, that if you take an alcohol that's a primary alcohol and you reflux it, you're going to go all the way to the carboxylic acid. So we're going to have that in there, and then you will have the C3H7 off the other side. I am going to put in CH2, CH2, CH3 for that. If you distill it, however, now they haven't put in that you'd be doing this at a lower temperature and you would be wanting to do everything you can to make sure that you isolate the aldehyde, but that's what they want. So the alcohol and the carboxylic acid with the OH groups, they're able to do hydrogen bonding and there's stronger, therefore, intermolecular forces, so they've got higher boiling points. However, the aldehyde that you first of all go through to get to the carboxylic acid, that one doesn't have as high a boiling point, so if you do the temperature below the boiling point of these two, you should be able to isolate our aldehyde. Okay, looking on at the other 2 reagents, we've got a carboxylic acid and H2SO4. The key bit you want to be looking at is the carboxylic acid, alcohol plus carboxylic acid in the presence of an acid catalyst gives you an ester. So I'm going to just take what it gives me here, CH3CO. Now, ester link looks like this, where you have the R group coming from the carboxylic acid and then the other R from the alcohol. So this is my CH3, the CO, and then what we want at this point is to think, right, how do I write this down to make it really clear? Well, I've started with the carboxylic acid, so I can write COO. That's going to be fine. Just be aware that if you write it the other way round, then you will go OCO if it goes from the alcohol first, and then, excuse me, CH2. If you do something like I've done there, just make it really clear that you understand that you've made an error. Don't leave something ambiguous in an exam. Okay, the last one with acid and heat, this is the conditions for dehydration of an alcohol, which means you're going to remove H2O. So we're going to take away the OH from here, and there's only one other carbon that we can take a hydrogen away from. What this is telling you is that you're going to be putting in, to make but-1ene, you're getting a double bond at the end, so make sure that that is clear in your answer. CH3, CH2, CH, CH2. Okay, over the page. So this is us on to the reactions of haloalkanes. Butan 1-ol can be prepared by the alkaline hydrolysis of 1-iodobutane we've got here, and it's asking us to use the Curly model to show the reaction mechanism. The key, it tells you, is the movement of the electron pairs. They start, the curly arrows start at the electrons. You've got to do the mechanism as shown, and then just go through and tick them off afterwards, all of the points they ask for. You want the name of the mechanism, the type of bond fission, and the relevant dipoles. Now, Up here, again, they've given us a structural formula. We really can't do this mechanism without using the displayed formula. So I've taken the carbon here and I've drawn it out. You could draw all the rest out, or if you want, you can just abbreviate that because nothing else is going on there. I'm also going to put in my other chemical. Now, the first thing to put in whenever you do organic reaction mechanisms is your lone pairs and your dipoles. The specific mark scheme for this question didn't need all of the lone pairs, but it's just good practice to put them in, and you can start thinking about which bonds are polar and where electrophiles and nucleophiles might be. So you've got hydroxide. It is most common to you as a base, however there is no acid-base chemistry going on there. So the presence of the lone pairs means it can also behave as a nucleophile. It is going to be attracted to electrophiles. Electrophiles, you're looking for something that's partially positive or positive. Well, the only thing we've got is the carbon, and here we have the iodine with lone pairs. Well, that is not going to be attracted or reacting with the OH. So there's only one place that we can put things together. So making sure that you start at a lone pair, curly arrow, and make it really clear it's going right into the carbon. If you've got small writing, make it bigger for a question like this. Make it really clear where your arrow starts and where it ends. So this is a bit like forming a dative covalent bond, except it would be giving this carbon a fifth bond. That can't happen. So the iodine starts pulling the electrons in the original bond away. Draw a curly arrow starting at the bond and going to the I itself. So it's a movement of the pair of electrons. So here we have a pair of electrons that were a lone pair and they come into the carbon atom. Here we have a pair of electrons that were a bonding pair and they go to the I. Whenever you're then working out the product, put in everything that has not changed first. So the C3H7 bonds to the carbon, no change. The two hydrogens, you do now have a bond to the oxygen. Again, you've got the product up at the top. You know that's what you have to make. And then you have iodide as the byproduct. So the way the marks were distributed for this is kind of given to you in the question. The very first thing it asks is that you include the name of the mechanism. We'll get to that. The type of bond fission, we'll get to that. Right, it wants the mechanism, the relevant dipoles. The delta negative I and the delta positive carbon got you the first mark. The second was for the curly arrow from the lone pair coming into the carbon. The third mark was for the curly arrow coming from the Ci bond. What's happened is this is behaving as a nucleophile. So this is nucleophilic. And what we've done is we've replaced the I with the OH, or we have substituted it. So this is nucleophilic substitution. And anytime you're using electrophiles and nucleophiles, the type of bond fission is heterolytic, because you have a different number of electrons going to each atom. So here there were 2 electrons in the bond, the I takes 2, the carbon gets 0. So that is heterolytic. Homolytic would be if you've got radical reactions. Okay, last part of this question. A student decides to prepare butan-1-ol by the alkaline hydrolysis of 1-chlorobutane. Suggest with reasons any change in conditions from those used in the alkaline hydrolysis of 1-iodobutane. Right, we've got 2 marks. Well, the first thing we're going to have to do is some sort of comparison. Previously, we used iodobutane, now we're using chlorobutane. The biggest difference is the halogen that we've got involved. If you look up at the example we had here, you had to break the Ci bond. We are now having a molecule where there's not a carbon to iodine bond, there's a carbon to chlorine bond, and so you just need to get in that the CCl bond is stronger than the Ci bond. And the most common mistakes here are when people don't do comparative answers. You are comparing these two things. You need to get in this idea. You could have put that it's harder to break or it needs more energy to break, but this is the crucial phrase. And now, going back and scanning the question, it wants us to think about any change in the conditions. Right, well, looking up, the only thing we get from the conditions is the reaction mixture is gently heated. Well, we now know that we're reacting a molecule that has a stronger bond, and so you're going to need more energy. If there is more energy needed, we're not going to be able to gently heat it, so therefore you would reflux. And looking up there, it said for 20 minutes, so let's increase that as well. Reflux for more than 20 minutes. You could have got away with putting that you would have to heat it more strongly, but reflux is the term you want to go for, linking back to what we looked at with the oxidation of alcohols beforehand. Thank you.